Hello, Hussam. So this is going to be my presentation for the last part of the book, Computer Systems: A Programmer's Perspective. Let's get into it. So, as we read the last part of the book, it is very clear what the purpose of the book is. It is simply proposing the idea that when people will code, the trial and error from coding is what determines their model for how computer systems work. But that model is naturally going to be decided by how much coding they did, and not in terms of time, how much coding time they did, but the breadth of the coding they did. So they could go their entire career without having coded a certain specific project, and they can go the entire career without knowing a specific problem. Whereas if they do have a theoretical map of how a computer systems work, they can then be much more prepared to write not only what is considered working code, but also correct code. And this is mainly done by understanding that there is a gap between what the computer seems to be doing and what it's actually doing. There is a certain hidden behavior that is hidden, so that we can make coding much easier, but it is necessary to understand so that you do not make certain mistakes. Previously, we have seen the inner workings of a program, so how programs work within themselves. We'll talk about compilers, about machine code, various other problems, or various others designs, and we have also seen how programs work inside the broader system, like how programs work inside the operating system, inside the OS. And essentially, in this section, we are going to tackle about the infrastructure that allows communication between programs, so how programs communicate with each other, and with not only between program to program, but also program to user, for example. And for this presentation, my approach is going to be very simple. I'm just going to give examples for each part of the book so that you kind of understand how it fits, because people tend to downplay or underestimate certain parts because they do not see the usefulness of it. So I'm just going to give examples to ground you and kind of make you infer why this section is important. And the broader presentation is going to work as a skeleton that will make reading much more easier, because you can then situate yourself as you read the book, rather than figuring it out as you go. So let's get into it. So the first part of the first segment that allows computers to communicate is the input-output system. And essentially there are two. There is the Unix input-output, and these are functions like read, write, open, etc. And we have the standard input-output. This is provided by the C library, and these are things like printf and scanf and other functions. And essentially in Unix, everything is a file, so we have a lot of files, but we also have metadata files and other forms of, but essentially they are files. And you do have operations like read and write, and these allow you to kind of modify everything. And the main revelation here is that reads and writes can sometimes return fewer bytes. This depends on the buffer, and this is just you cannot avoid this bug. It is not a bug, it is simply how the system is. And actually the best reaction is to call read again, but most people don't know this, and they kind of just either work with missing information or work with erroneous information. This is kind of the example of why knowing these things is going to be useful. And also the standard IO does provide printf, which is a lot more rigorous than the Unix read, but it is also can lead to problems in buffering, so it is generally superior to, like, the Unix interface is generally superior than the standard interface. Moving on, we move about network programming. And the networking is essentially there is a local network, and this local network is wired there is an actual connection between each machine, physical connection between each machine, and each machine is identified by a MAC address. And this system is unreliable, so if the local network is not switched, everybody can listen to every packet moving on, and the packets also just have a MAC address, so an IP address, so they're not so there are no double checks, if you want to call it that. And the next layer of abstraction is networking protocols, for example TCP or UDP, and these kind of provide solutions to forward reliability. So there is acknowledgement, so a receiver can acknowledge that they did receive a packet. If not, then the sender needs to retransmit the packet, and each packet is also going to be sequenced in number, so that the receiver, even if they receive packets that are unorganized, they can reorganize them, and various others methods. You get the idea about how these networking protocols work. And you have sockets. Sockets are essentially the interface that programs deal with, and these sockets are essentially just open socket. You listen, you accept connection, and then you can communicate for a little bit, and you close. Sockets are just an abstraction themselves, so they're an idea to be implemented. The revelation for this networking program, for the network programming part, I think it is best served by the book. The book kind of at the end provides a simple server, simple HTTP server, and in doing so kind of mixes everything together, and also mixes parts about because going back to the previous example here in the how this read and write returning fewer bytes can be a problem, because when you run this problem locally, it is not a problem, because at the end of the day it's still one program and a relatively reliable network. But when you move to a broad network that can be stressed at times by high traffic, that you are potentially working with adversaries in the network, people are trying to attack you, and knowledge of these problems is going to be clear. So this is just a kind of, I'm saying this information to motivate you, because I did say I'm going to provide examples, but in this case I'm not providing an example, because I believe that the greatest example is the simple server at the end of the chapter. And moving on to concurrency. Concurrent programming is simply that programs running alongside each other, and there are essentially three models of concurrency. There is a process base, so each program has its own process and everything that comes with that. There is multiplexing, which is a single process that is handling multiple connections, so they do have the same address and everything, but there's multiple file descriptors that the process is keeping connection with, and this is kind of what allows concurrent execution of programs. And there is a thread based, and this is the one that the chapter goes deep into, and these are multiple threads sharing the same address space, operating at the same time. And the main danger here with the thread space is something called the race condition. So where a program is waiting for a certain condition, but the other program is also waiting for, like program A is flagging condition A, but is waiting for condition B, but program B is flagging condition B, which waiting for condition A, and they kind of wait on each other. So you kind of have to synchronize, and this comes with various problems. And the summary is that thread based is generally best, because there is no single best model, and in reality you are going to use all models on the same program. They're just depending on what you need them to do. So thread based is best when programs need to share data and communicate, and because the problem with the thread based is that you need to be more rigorous when it comes to synchronization. And if you are willing, if it is important for you to have a mechanism for communication between programs, and you are willing to be asynchronously rigorous, then this is going to be your best bet. Process based is best when isolation is more valuable. This is for security reasons than communication speed. And multiplexing is best when concurrency is going to be IO bound rather than CPU bound. So what you want to concur is going to be mainly on the IO sector, not about the CPU performance. And this is it. This has been my presentation. Thank you for listening.